All right, going over the warm-up question for today. It says a survey was conducted to determine the probability of students eating school lunch. 200 students were questioned and 128 responded that they regularly eat school lunch. Based on this data, what is the probability that a student doesn't eat school lunch? What type of probability are we talking about? Experimental, right? When we use actual data that we've collected. Okay, so the probability that they don't eat school lunch how would we set that up? Okay, I'm hearing 72. Where are you getting the 72? Okay, so 200 minus the 128 is 72. All right, and that's the number that don't eat lunch? Okay, so we would have 72 out of 200. Can we reduce that? What do you get if you divide them both by 2? Bless you. 36 out of 100, so it would be 36%, right? Out of 100 would be percents. So we have a 36% probability that the students do not eat school lunch. Then the second question says, if there are 2,400 students in the school, how many should we expect to not eat the school lunch? What are we looking for here? Okay. So we're taking 36% as a decimal would be 0.36, and we're doing what? Yes. Multiplying it to 2,400, and what do we end up with? Okay. All right. We started talking yesterday about probability. We looked at experimental and theoretical. Experimental is what did happen, right? Based on data, observations, simulations, something like that. Theoretical is what should happen, right? If everything was perfect, what should happen? We are going to continue with probability. It involves, a lot of the questions you're going to see today involve using a deck of cards. So I just wanted to quick review a standard deck of cards. How many cards are there? Okay. How many suits? Have you heard that term? Suits? How many suits? 4. All right. Clubs, spades, hearts, diamonds? Okay. How many different face cards? What do we mean by a face card? Jack, Queen, and Kings. Yep. So how many face cards are there? 12 face cards. Okay. Does that make sense? 3 types, Jacks, Queens, Kings, but total of 12 in the deck? Okay. All right, so it often is easier to use combinatorics, new word for you, combinatorics, to find theoretical probability rather than listing and counting all the equally likely outcomes. Yesterday we talked about rolling a die, right? What's the probability of rolling a 4? Okay, well that was small sample space, right? 1, 2, 3, 4, 5, 6 is your sample space when you roll a die. It's pretty easy just to look at them and count. Okay, but when we're starting to talk about like hands being dealt out in a card game, we've got a lot more possible hands to be dealt, yes? So instead of trying to list all the different options and count them that way, we're going to use combinatorics. Combinatorics include the fundamental counting principle and ways to count permutations and combinations. Most of what we're going to be doing will be using combinations, because when I deal out cards, does it matter what order you're dealt the cards? Usually, depending on the card game you're playing, you rearrange them in your hand, right? So the order the cards are dealt doesn't really matter. So we're looking at more of a combination rather than a permutation. Our first one says, what is the theoretical probability of being dealt exactly 2 sevens in a 5-card hand from a standard 52-card deck? Okay, now, the most common mistake is students focus only on the fact that they need 2 sevens. But you're going to be dealt 5 cards, right? And if you have to have exactly 2 sevens, that means your other 3 cards can't be a 7, right? So you have to look at both of those things together. How do you get 2 sevens, and how do you get 3 that are not sevens? Okay? When we set up our combination, the first number, we usually think of it as NCR. That first number is going to be how many are available. So if I'm talking about sevens, I want to know how many sevens are there in a standard deck. Okay? So the first number is going to be what is available. The second number is how many you actually want. Okay? So instead of thinking NCR, think available, C, want. Okay? How many are there in the deck, and how many do I want in my hand? Okay? So we are going to look at 2 situations here. We want how many sevens? We want 2. Okay? The other 3 cards in our hand can't be sevens, right? So we need 3 that are not sevens. And for both of those 2 things to occur together, to have 2 sevens and 3 something else, we're going to be multiplying. Okay? When we talk about probability, we're always looking at the denominator being the total sample space, right? Okay? So we're going to be dividing by total number of 5-card hands. Okay? Now, if you think of 52 cards, there's a lot of different combinations you could come up with, right? To have 5 cards. So this is why we're not going to list them all and try to count them. Okay, so we've got our basics set up. Now we're going to convert them into combinations. So for the sevens, how many sevens are available? 4. How many do I want? 2. Okay, and I need 3 that are not sevens. Okay, so for my next one, I want 3 other cards. So if there are 4 sevens in my deck, how many cards are in the deck that are not sevens? Does that make sense? So we have 48 cards available that wouldn't be a 7, and I need 3 of those. Does that make sense so far? Okay. Now, how many ways can I get a 5-card hand? Well, how many cards are available? 52. And how many do I want? I want 5. So denominator would be 52C5. Questions on that setup? Okay, so in the numerator, we're using that idea of the fundamental counting principle. So the first piece here, this is all the ways I can get a 7, or sorry, 2 sevens. Second piece, all the ways I can get 3 that are not sevens. Yes? Fundamental counting principle says we multiply those together. That's all the different ways that I can get a 5-card hand with 2 sevens. And then for the probability of it, we have to divide by the total number of 5-card hands. All right, so we're going to grab our calculators. All right, so we have 4C2 times, oops, what do we have, 48C3 and then we're going to divide by 52 C5. Okay? All right. Did you get 0.0399, etc.? Okay. Now, what is that as a percent? What do we have? 0.0399? So we have 3.99, about 4% chance of getting a 5-card hand that has exactly 2 sevens. Okay? Our next question says, what is the theoretical probability of being dealt all 4 sevens in a 5-card hand? Okay, so keep in mind we have to account for all 5 of our cards, right? So we want 4 sevens, which means we need what? What else? One other card that is not a 7, correct? Okay. All right, so how do we get 4 sevens? How many are available? 4. How many do we want? 4. Okay, and how do we get one that's not a 7? How many not 7s are in my deck? 48. And we want 1. Okay, compared to all 5-card hands, 52C5. You should be able to recall your last question or the last thing you typed in your calculator, right? And just change a couple of those numbers. All right, so second entry, recall that, and we need to change that to a 1 and that to a 4. Yes, 4C4 times 48C1 divided by 52C5. What number is that? Notice the E -5 on the end. What does that mean? It means our decimal is really 5 spaces to the left, right? We have a very small number here. So we are looking at, what is it, 0.0000185? What would that be as a percent? What do we do when we convert to a percent? Move our decimal over to? So we'd have 0.00185%. Very, very, very small chance that you are dealt a 5-card hand and it has 4 sevens in it. Okay. Our next question says 6 of the 34 players on a football team are left-handed. There are 5 starting offensive linemen. So we have 34 players and there's 5 that are going to be the starting offensive linemen. What is the theoretical probability that 2 of those are left-handed? Okay. So what is it that we need? Let's start with our total. How many total on the team? 34. And we want how many? 5, right? We want to make a lineup of 5. Okay. So our denominator would be 34C5. That's all the different ways we can take those 34 players and put them in a group of 5. What makeup do we want for that group? Of those 5 players, we want 2 of them to be left-handed? Okay. So, how many left-hand kids do we have? And we want 2 of those? So, how many are right-handed? (34 minus 6). Okay, so we have 28 that are right-handed, and we need how many of those? 3? All right, so how do we set up the top part of our probability statement? 6C2, that's how we have 6 left-handed players, and we want 2 of them, times, okay. All right, go ahead and grab your calculators. I'm going to pause it for a second so you can figure that out. All right, so calculating that, you should end up with 0.1766 as a decimal. which would be about 17.7%. Okay. What is the theoretical probability of selecting a group of 2 boys and 2 girls from a class of 32 students where there are 18 boys? So I'm going to pause it for a second. I want you guys at your tables to talk about what is it that you have available, how many do you want, get it set up. All right, so how many kids are we putting in a group? 4. We want 2 girls, 2 boys? Okay, how many boys are in the class? How many girls? And so the total? 32. All right, so how do we show that we want 2 girls and 2 boys? So to get 2 boys, we would do 18C2. To get 2 girls, okay, and the total ways we can make a group of 4 kids. Good. All right, what did you come up with for a percent? Good. All right, questions on using combinations to find probability. Now, you can, the ones that we've done, we had 2 things on the top in the numerator, all right? But I could say I want a 7-card hand, okay? And in that 7-card hand, I want 3 face cards and 2 5s. Okay? I want 3 face cards and 2 5s. What's the probability of me getting that? How would we set it up? Have I described all the cards that I want, or that would be in my hand? I've described 5 of them, right? 3 face cards and 2 5s, and we had a 7-card hand, so there's still 2 that are what? Okay. All right, not 5 and not a face card, correct? Okay, so let's start building it. How many face cards did we say we had in a deck?
12.
Face cards. 12? Okay, so we have 12 face cards available, and we want 3. Okay, then to get my 5s, how many are available? 4, and I want 2. Okay, then I need 2 more cards that are something else, right?
Yes.
Okay, so I want 2 more. I have 52 cards, and I can't use the 12 face cards. So now I'm down to 40, right? Then I take out the 4 5s. So I'm down to 36 cards available that aren't those things. Plus 2. Does that make sense? What would the denominator be? Yes, 52C7. Now I want 7 cards in my hand. Does that make sense? So you can string a whole bunch of pieces together on the top. Okay. The last little piece that we need to talk about, I mentioned it a little bit yesterday, it's the geometric probability. All right? And it's just using a geometric concept to count. All right? So instead of counting like how many ones do we roll with a die, we are looking at counting maybe the area or the volume of something. Okay? So in this case, it says, a batter's strike zone depends on the height and stance of the batter. What is the geometric probability that a baseball thrown at random within the batter's strike zone will be a high inside strike? Okay? So the whole strike zone is this grayish part, right, with the yellow border. We're looking at what is the probability it lands in this top little red corner. Okay? So we're using area. We want to compare the area that's shaded in red compared to the whole strike zone area. Does that make sense? Okay. So we need the red area. Area of red section compared to the total area of the strike zone. So, what would be the area of the little red section? What are the dimensions? It's 4 by 6, right? So it has an area of 24. What's the area of the whole big strike zone? Dimensions are 17 by 22. Okay, so we're basically saying we're going to take 4 times 6 and divide by 17 times 22. Okay. Make sure if you're going to type it that way in your calculator that you put the 17 and the 22 in parentheses and use a multiplication symbol in between instead of each individually in a parenthesis. Okay? Go ahead and figure out what that probability is. All right, I'm seeing 0.064 for a decimal. So it would be about 6.4%. Okay. Last one. Suppose a batter's strike zone is 15 by 20 inches and the high inside strike area is 3 by 5. Figure out the probability of landing in that high inside strike zone. All right, shouldn't need a calculator for this one. What's 3 times 5? 15. There's a 15 in the numerator and a 15 in the denominator, right? So this 15 will reduce with that one. We get 1/20th, which is what? 5%. Could I also have asked you for the probability that they're not in the high inside strike area? What would I do differently? So, if I don't want to be in the high inside strike zone. If there's a 5% probability that I am there, then there's a 95% probability I'm not. Yes? Okay. What if I hadn't calculated that 5% already? Okay, in other words, I hadn't given you the first question, we went right to that second question. What could we do? Okay, so the 15 times 20 is 300. So she said take the whole area, subtract the little red section we don't want, right, which was an area of 15, and compare it to the whole thing. Does that make sense? Okay. So you guys will be working on using combinatorics to calculate probabilities and also doing some geometric probability.